Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to look at what happens when you take the integral of an area that's defined by multiple functions. So there are a couple of scenarios that we're going to look at in this section. And the first one is honestly very simple and about as straightforward as you would expect it to be, which is the area between two curves. And this comes up in a couple of different ways. The top one would be you simply have an area that is either above or below your x-axis, and it's bounded by two curves. And it's exactly what you would expect. You simply, instead of stopping at the x-axis, you have a curve that is either the bottom or the top. And if you think about how we found the area originally, all you do is instead of having your x-axis be here and you have a nice flat straight area, you just have to have your bottom bound be a curve. And if you go in and draw your Riemann sum and then think about what that looks like geometrically and then build that Riemann sum, you see, oh, well, okay, yeah, that's pretty easy. All I'm doing is taking this exact same idea because now I'm looking at, okay, what are my rectangles or what are my trapezoids? Well, my height is my top curve minus my bottom curve because it's just this xi minus that xi times whatever my width is. Okay, so I put that in here, and then this is exactly the definition of this integral, so, oh, okay, it just becomes this. And then it doesn't really matter if your axis goes in between, because even if you were to break this up into an integral above the axis and an integral below the axis and add them together, it ends up being the same thing. Because remember, this is going to be negative. And so if you break this up into f of x plus the g of x here, this is just plus the negative g of x, which, yeah, that's going to be the exact same thing. So either way you look at this, it ends up working out, and you can do it either way, and you get this exact same answer, right? So this one is pretty straightforward. But what happens if they cross each other? What's going to end up being the situation there? And well, it actually turns out that when you think back to when we talked about the situation where your function crossed above and below the x-axis, you can probably figure out the answer to that as well. And it's just a simple modification of what we already have written here. So see if you can figure it out before I show you. So if you assumed that we would be using absolute value just like we did before, good job, because yeah, that's exactly what we're doing. The entire purpose of absolute value is to create that piecewise function that's going to allow us to flip around the equation whenever the g of x is larger than the f of x, or in this situation, whenever the g of x is above the f of x. So what that means for us functionally is that we need to figure out where do the functions cross, and when they cross, we'll need to flip around the f of x and the g of x, effectively breaking up our single integral into multiple integrals so that we can then do the integration. So in the case of this one, because we have it crossing at C and D, and if we knew what the functions were, we'd have to figure out where those points were. Then what we would do is we would say from A to C, we go f of x minus g of x. And then from C to D, it'd be g of x minus f of x. And then from D to B, we're back to f of x minus g of x. And you just have to kind of figure out where and when you need to flip your functions around. And it doesn't matter if your function is above or below the x-axis or what's going on, as long as you have your situation set like this. And if you have a more complicated situation with multiple functions, you're effectively going to have to look at that graph and break it up into pieces. And in the end, that is how you're going to have to handle this. A lot of the more advanced calculus really comes down to looking at the behavior of the graph, looking at the behavior of the function, and trying to utilize your technology or utilize your understanding of what functions look like and how they behave in order to help you understand how you're going to have to handle the calculations. There is a very large relationship between what we do on paper and with calculations, and with how we help ourselves with our technology when we start to get into more advanced math. Yes, you can do things by hand, but you really, really do help yourself out when you learn to use your technological tools. So we're going to look at one more situation and then a way that it leads us to a different kind of integration. So the last scenario we're going to look at is one where it's either a matter of convenience or kind of a matter of necessity. Now, you don't have to use what I'm calling vertical integration, but it does help you out, and honestly, there are many situations where it will be significantly easier than trying to contort things around in order to continue to use normal integration. Okay, so when I call it vertical integration, what I mean is instead of integrating along the horizontal axis, we integrate along the vertical axis. And when we do this, we think about this in inverses, because what we're going to do is we're going to take something where we have it defined in x, and we're going to simply use the inverse function, or we're going to use the function as defined by y. And so in the first example, we actually can just go ahead and do the normal integration, but we would have to split it up at this point and integrate this piece and then add them together. But if we integrate along the y-axis instead, integrate vertically, then we're actually able to just integrate from here to here and then go from C to D to this point here. And then the only thing we need to worry about here is what's going to be the top of our curve and what's going to be the bottom. And this is why I say you need to think about it in inverses, because remember, when we think in inverses, you think about reflecting across the line x equals y. So whatever is down here is going to flip to up here, and whatever's over here is going to flip to here. So it kind of flips like this, right? So this side is the bottom, and this side is the top. So when we define this, all we do is we say if u is a function of y and v is a function of y, u is our outer curve and v is our inner curve, we want u of y to be greater than or equal to v of y. So basically we want the right side to be bigger than the left side. That's it. And then we set it up the exact same way we did before. And in the same way, if we have them crossing, we simply use our absolute value. And you'll find your area, because you'll notice we drew it the exact same way. And so in this situation, it's a matter of convenience. Down here, it's also a matter of convenience, but also almost a matter of necessity. Because if you were to try to do this one using integration along the x-axis, you would end up having to take these graphs and then translate them down and then integrate them as a part below the x-axis, a part above the x-axis, and add them together, specifically because at this point here, you cannot do the normal integration because you would be integrating this curve on itself, and our integration method just doesn't allow for that. So it becomes kind of an issue where here, you basically have to integrate along the y-axis instead. So there you go. Let's go ahead and leave you with a couple of exercises to practice these, and that'll be it. This is the final video in the introductory course for calculus. The intermediate series is going to cover topics such as volume integration, advanced integration techniques, exponential and logarithmic equations from a calculus viewpoint, as well as differential equations. If you need any additional assistance, remember you can always drop into the comments or join us on Discord, and as usual, the answers to the exercises will be after this outro.